Okay, we'll start from current slide. And we finished example 2, and we're starting example 3. So let's do example 3 right here. Any questions on anything before we get started? Goodness gracious. All right. Example 3. On page 90, determine all the vertical asymptotes of the graph h of x is equal to x squared plus 2x minus 8 divided by x squared minus 4. All right, what would be your approach to a problem like that? Where would you begin? Let's factor everything in sight, okay? So, does that numerator factor? That's the big question. I know the denominator does, okay? And frankly, when I do this, I go on and factor the thing I know will. So let's factor that denominator first. What would that factor as? A little louder? X plus 2 times x minus 2. Okay. Now, the reason I did that is if the numerator won't factor into one of those, then it's immaterial because nothing's going to cancel out. So let's try first x plus 2 and see if that will factor. I don't know if it will. This is just trial and error. Okay, if it did, what would this factor have to be, that first term? It would have to be an x, and it would have to be a minus. You're absolutely right. And the only thing it could be would be a 4, right? But that second? Yes, but then you would have a negative in the 2x here. So obviously that won't work. So let's try putting the minus there and the plus there. And let's see if that would work. All right, let's give it a shot. And what do we get? X times x, x squared, plus 4x, minus 2x, that's plus 2x, minus 8. Yes, it works. Okay, now what? Yes, divide out the x minus 2's. Okay, so whereas when you first looked at this, if you'd have jumped to the fact and said, oh, it has a x plus 2, x minus 2, it has 2 vertical asymptotes. No, it doesn't, because one of them will divide away. Okay, so it only has one, and what is that vertical asymptote? That's what it asks us for. Determine all vertical asymptotes of that graph. What would it be? X equal, I like to actually say x cannot equal negative 2. You can say it the other way if you want to. That says it cannot happen, okay? X cannot be a negative 2. Now, they're going to take it another step. They've got something wrong in the book. I don't know if any of you noticed that. They say x cannot equal 2. Yes, it can equal 2. No problem with it equal 2. That should be a minus 2 there. X cannot equal a negative 2. Okay? And all x values other than x equal 2, wrong. X equal negative 2. The graph of h coincides with the graph of x plus 4 over x plus 2. So you can apply the theorem and conclude there is a vertical asymptote at x equal negative 2. They got it right there, okay? I don't know. Actually, x can't be 2 either, so they sort of had that right, but it can't be negative 2 as well, okay? I would have said both of those. In fact, I think I will put that in. X cannot equal -2 or 2. Okay. But the x equal 2 is not a vertical asymptote. There's your vertical asymptote, but x can also not equal +2, but that's not a vertical asymptote. How do we draw that one? Okay. This is the vertical asymptote. This is just a place where it doesn't have a value. So let's just start ticking off. 1, 2, 3, 4, 5. We don't need that many. That's negatives. 1, 2, 3, 4, 5, 6, 7, 8. Positives. 1, 2, 3, 4. Negatives. 1, 2, 3, 4. Okay? How do we place things here? If you were asked to graph that, which you might be at some point, I can't get my red ink to come on. There we go. So where's your vertical asymptote? Okay. X cannot equal -2. So I like to draw vertical asymptotes in red. Now, since we're here anyway, and I'm drawing in red, does this have a horizontal asymptote? Where? Okay. Not 4. Okay. The horizontal asymptote is the ratio of the leading terms. What's x squared over x squared? 1. Okay. There's your horizontal asymptote at y is equal to 1. Okay. So now we got our asymptotes in there. Vertical, it can't cross. The horizontal, it could touch or cross, but it's there. Okay. So where do we go from here? How would you go about graphing that? Say again? Well, there's another really easy point to graph. I'm going to go back to my dark color here. Real easy point to graph. Say again? Okay. X equal +2. What would its value be? So h of 2, knowing it can't be 2, but that would approximately be, or that's not really even the right term for it, what would that be? Plug it in, plug it in. Well, okay. Now, you said something else there that would probably work. Since you said 2, 2 plus 4 is 6, over 2 plus 2 is 4. 6/4 is 3/2, right? Okay? 3/2 is 1 1/2. So there is your hole in the graph, okay? At 2, 1 1/2, okay? Now, the other point I was sort of digging for, real easy to plug in, x equals 0. What do you get if you do x equals 0? What's h of 0? Now, this isn't equal here. What would that be? Not that hard. Plug in a 0 here and here. 2, okay? So x, that's your y-intercept right there.
That's what I was saying.
Oh, is that what you're...
Yeah, you start the triangle at 2.
Okay. Okay, I see what you're saying. I don't hear well, so I didn't catch what you were saying. So since we know it's going to the vertical asymptote in this direction, has to pass through this, acts like it's going to pass through there, and then approaches a horizontal asymptote, that's that end of it. Well, we still got to figure out what's going on to the left of the vertical asymptote. So what might you do next? That, by the way, was 2. Okay? What might you plug next? Remember, you get to choose your x. Choose one. I'll tell you two not to choose, plus 2 and minus 2, because or 0. We've already done that. But what would be a good one to let you know what else is going to happen here? How about x equals -3? So plug that in and see what you get. H of -3 would be, plug it in there and there. Okay, it'll be 1 on the top, and what's on the bottom? -1. So that's going to be -1. So x equals 3, y is equal to -1. Ha! I think we've got it pegged now, because this now, I thought you were saying this before. When x is equal to -4, this obviously comes out x equals -4? 0. Okay, so there's another point. So x equals -4, that's a 0. Okay? Yeah, this says that indicates it's approaching the horizontal asymptote in the long run, has to go through those 2 points, and then has to go to the approaching negative infinity in that direction. So the only vertical asymptote was x equal -2. Or actually, I like to say x not equal -2. X equal 2, the function's not defined there, but it's not a vertical asymptote. It's a hole in the function, hole in the graph, right? Does that make sense? Got it? Okay, so when you can, factor, okay? Now, they write some other things down which are fine. The limit as x approaches 2 from the negative side goes to negative infinity. We see that. And x approaches 2 from the positive side goes to positive infinity. To me, yeah, it's fine to say that, but those are not limits. It has no limit. It's going to an infinity, okay? But they phrase it that way. All right, any questions on that? All right, let's go to example 4. I am feeling better than yesterday, but still not great. I mean, Monday, but still not great. All right, here are a couple of other limits. What is the limit as x approaches 1 from the negative side of x squared minus 3x over x minus 1? Okay? And then we'll also do a limit as x approaches 1 from the positive side of the same thing, x squared minus 3x over x minus 1. All right, what's going to be your approach on a problem like that? Say again? Plug it in. Let's see what we get. What do you get in the numerator on this one? X approaches 1 from the negative side, so let's just put it in 1. That would be 1, which would be over 0. Well, guess what? It doesn't approach anything. It's an undefined form. That's not an indeterminate form, 0 over 0, not at all. It's not. So this is going to an infinity. The question I think that they really want us to know is which infinity is it going to, okay? So what I would do here is, if it's approaching 0 from the left, from the negative side, approaching 1 from the negative side, let's let it go to 0. What does 0 give you there? If you plug in a 0 for x. 0 over -1. Okay, that's 0, but it tends to be a bit on the negative side, right? So maybe let's do 1/2. Let's do that. That's closer to 1 and it doesn't give you a 0. So what does this give you? 0.25 minus 1.5, that would be negative 0.75. Okay? And this would be negative 0.5. The point here is going to positive. That would be negative, that would be negative, negative over negative is positive. And so I would say this is going to positive infinity. Okay, this is what they're looking for. Okay, let's do it from the right-hand side. And let's do the same type thing. There's no reason to plug in a 1. That's going to give you a 0 here and not a 0 there. And let's not do a 0 either, because that's going to be 0 over a negative number. So let's do, say, 1 1/2, 3/2. What would this be? 3/2 squared. 2nd? 9/4, is that what you said?
I said 6/4.
6/4, I think it's 9, right? Yeah. Yeah, 9/4. Minus, you're plugging in a 3/2. 2nd, that would be 9/2, right? So that would be a 9/4 minus 9/2 would be negative 9/4, right? This would be 3/2 minus 1, that would be 1/2. Am I doing this right? Doing it all in my head, and I may be making an error. Yeah, that would be a negative. That would be going to negative infinity. So this, and I don't like to write it this way because it makes no sense, but sure enough, that's where it's heading. Okay. Now, that's what they were looking for. Now, this is a slightly different kind of problem if we were to graph it. Did y'all do this in Math 112? I don't think we did. This was one of those things we call a slant asymptote. Okay? It does have a vertical asymptote at x equal 1, obviously. Vertical asymptote at x equal 1. Going to positive infinity from the left, negative infinity to the right. But because the numerator is 1 degree greater than the denominator, you could divide the denominator into the numerator and have a line. And that's going to be x. I can tell that's going to be an x. So that's going to model the a slant asymptote. It won't have a horizontal asymptote, but it'll have a slant asymptote with a slope of 1. Okay? They didn't ask us for that, but I just wanted to point that out. If you see it in the book, you'll see that's the case. Okay. Now, they have a technology pitfall at the bottom of the page 90, and it says when using a graphing utility, like a graphing calculator or something, be careful to interpret correctly the graph of a function with vertical asymptote. Some graphing utilities have difficulty drawing this type of graph, because it's trying to connect dots that don't connect. One's going this way, one's going that way. It tries to connect them. They don't connect. They do not. Okay. Any questions? That's all they're looking for here. To me, it doesn't have a limit. It says find each limit. It doesn't have a limit. Yeah, one's going to infinitely large and one infinitely small, but those are not limits. Okay. So anyway, let's move on to this. Okay, top of page 91, properties of infinite limits. Which are not limits at all. It just frightens me, but they talk about them all the time. So let's C and L be any real numbers. Look sort of familiar, don't f and g be functions such that the limit of f of x as x approaches c, any real number, is a positive infinity, and the limit of g of x as x approaches that same c, any real number, is actually the value f. Okay? Now, it's kind of crazy, okay? Because the limit of a sum or a difference is going to be the sum or difference of the limits. This one's going to infinity, that one's got some fixed value. When you add an infinite number to some fixed number, it's still infinite. If you have an infinite number and you're subtracting the fixed number from it, it's still infinite, okay? So that's why the sum or difference formula is like this. Now, if I had these reversed, L was here and the infinity was there, then you have to, if it's plus, that would be plus. If it was a minus, a subtraction here, then that would make it negative. So why even do this? I don't know. It's kind of crazy. Now, how about product? So the limit of a product of two functions, this one has no limit, and this one does have a limit. Guess what? You multiply an infinity by any number, you still get an infinity. Okay? That's if L is greater than 0. But if this L happened to be a negative number, then you have negative infinity. So what's the point of doing this? You can't really tell. It's just that there is no limit. If one of them doesn't have a limit, the sum, difference, or products don't have limits. Now, this is the one that might matter. The quotient, the limit as x approaches c of g of x over f of x, that's going to be 0. Because your denominator is going to infinity, so therefore some fixed value, L over infinity, is always going to be 0. Now, if they reverse those and put the f of x here and the g of x there, that would again be infinity. Okay? But it's 0 if the finite limit is on top and the infinite limit is on the bottom. Similar properties hold for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity. So you do the same thing there. All right. And here we have Elijah. All right. Good deal. Any questions on that? They do have a little proof here. I don't think the slideshow shows the proof. They just jumped to example 5. This is on page 91. Okay. Now these are some things that we've already hit before. What's the limit as x approaches 0 of the number 1? 1, of course. 1 is always 1, no matter what x is approaching. Okay, what's the limit as x approaches 0 of 1 over x squared? Say again?
I say indeterminate.
I can't hear.
Indeterminate?
Not just indeterminate. It doesn't exist. And it's going to positive infinity because this is always positive as x goes to 0. So that's going to positive infinity, which isn't a limit. Okay? So what happens if you add 1 to 1 over x squared? Still not going to have a limit because you're adding 1 to an infinite number, which is infinite. Okay? To me, these are kind of crazy. Okay? But that's what you got. This has a limit. That does not have a limit. So the sum does not have a limit from that previous property we just did. Okay? The B one here, we're using, okay, what is the limit as x approaches 1 from the negative side of x squared plus 1? Yeah, plug in a 1. 2. That goes to 2. Okay, now we're doing limit as x approaches 1 from the negative side of cotangent pi x. In other words, plug in a 1 and you get cotangent pi. Yes, exactly.
So, and
Yes, and actually it would be a negative infinity because it's approaching it from the negative side. Yeah, so it's going down real fast. So that's negative infinity. So what do you have if you combine these two? X approaches 1 from the negative side of x squared plus 1 over cotangent pi x. Well, this was 2. This was going to negative infinity. Something over infinity is going to 0. Okay? So this does have a limit going to 0. Okay. So perhaps there's some value in doing some of these, especially that quotient. The sum, the difference in the products, they're going to infinity. The quotient, if you have the infinity in the denominator, then it's going to 0. Infinity in the numerator, you can't tell. Okay. Good deal. Any questions on that? Let's see if there's a C one here. Yeah, here we go. What's the limit as x approaches 0 from the right-hand side of 3? 3, okay. 3 is 3, no matter where you're approaching, okay? And the limit as x approaches 0 from the right-hand side of cotangent x. Where's that heading? Positive infinity, exactly, okay? So, what if you did the product of those two, 3 times cotangent x, that would be 3 times infinity, that's infinity. There's hardly any, as far as I can tell, practical application for this. This one has some, because you put infinity in the denominator, it's going to 0. Okay. That's the only one that seems like it's even worth wasting your time over. Okay? So let's go to D. Okay? What's the limit as x approaches 0 from the left-hand side of x squared? As x is going to 0. Plug it in, plug it in. 0! Okay, limit as x approaches 0 from the negative side of 1 over x. That's your negative infinity, okay? So what do you do if you add those two together? A 0 plus a negative infinity, negative infinity. It can't be anything else. So what's the point? I don't know. Okay. Make sense? Okay. And guess what, folks? That finishes 1.5. So homework exercises here. I've assigned some of these before. Do either 3 or 5. Both of those are at calcchat.com. 3's at calcview.com. Do either 7 or 9. Both are at calcchat. 7's at calcview. Do any of the odds 11 through 15. They're all at calcchat. None of them are at calcview. Do any of the odds 17 to 31. All those odds are at calcchat, but only 25 is at calcview. Do either 33 or 35. Both are at calcchat. 33 is at calcview. Do any of the odds 37 to 49. They're all at calcchat, but 41 is at calcview. Do 51. The only one like that is at calcchat, not calcview. And do 53. It's at both calcchat and calcview. And then if you want to think about, explore the concepts of 57, 55 or 57 or both, that's up to you. I'm not going to require those, but if you find them useful. 59 is another one that's 4 parts. You could take a look at that. Rate of change, that's usually a pretty good physics problem. Many of you going to go on and do physics? Yes, I figured you might. So not be a bad problem to look at there. 63, another one to look at. You might, not want to waste too much time on it or spend too much time on it, but it's a pretty decent problem. Then they have some true-false. Any of the odds, either 65 or 67. I assume those are also at calcchat. They may not be. I'll let you investigate that. I don't know if the answers are in the back either. And then there's some finding functions, 69, a proof at 71. You decide whether you want to follow up on those. And then infinite limits, 73 or 75. I would assume both of those are at CalcChat. However, they say use the epsilon delta definition of limits to prove the statements. Again, I don't really care for calling them infinite limits. That means they don't have a limit, so to me that's a little bizarre. All right, now we have finished chapter 1. They do have some review exercises here, so again, I'll suggest to you, you can do, I know you can do the odds here. I don't recall if the evens have answers in the back or not. They don't? Okay. On review exercises. So you can do number 1 if you'd like, number 3 if you like, number 5 if you like, either 7 or 9, any of the odds 11 through 27, 29 or 31. And by the way, all these are at calcchat.com. It doesn't look like any of these are at CalcView, but they are at CalcChat. Okay, I said 29 or 31, 33 or 35, 37, any of the odds 39 to 49, 51, 53 through 57, 59, any of the odds 61 through 65, 67, 69, 71, any of the odds 73 to 77, 79 through 87, and 89 is a pretty decent problem to look at. Now, if you're really into some problem solving, the page 97 is a fairly involved problem, but calcchat.com has tutorial help for that. So if you're really into it, that would not be a bad thing to look at. That's 97 and 98, pages 97 and 98. And it's odd number exercises of those. So it's 1 through 13. All right. Now, any questions on chapter 1? Limits. And when you see the test, it's basically all limits. I mean, not quite, but pretty close. Any questions on your limits? And again, those extras that I did at the end, only if you need to do those do you have to, but if you find some of that enlightening, useful, by all means go for it. All right, now to me, this is where the real calculus begins. I mean, limits are necessary, they're there, but this is differentiation, this is differential calculus, okay? And we're letting this get started. Do any of you have to leave early today? I want to get your test before you leave, so just let me. Well, okay, there we go. So let's go to differentiation. So 2.1 is going to talk about the derivative and the tangent line problem. Okay? Now, I think we talked a little bit about secant lines and tangent lines in chapter 1, didn't we? I've taught from so many different books. I can't remember if they brought that up or not. But that's what we're going to... No, we didn't? Okay. All right. Well, then we'll hit it now. We'll find the slope of the tangent line to a curve at a point. Okay? We'll use the limit definition. See, we're not getting away from them. They're still there. To find the derivative of a function. And they say you'll understand the relationship between differentiability and continuity. They're similar, they're related, but they're not quite the same thing. Okay? A function can be continuous and not be differentiable. If a function's differentiable, it's got to be continuous. Okay? We'll get there. So let's start with the tangent line problem. Calculus grew out of 4 major problems that European mathematicians were working on during the 17th century. That's the 1600s, way back then. One of these was the tangent line problem. Okay? Another was the velocity and acceleration problems. Okay? Another was maximum and minimum problems. And another was the area problem. Okay? Your derivatives deal with the first three. Okay? Your integrals deal with the fourth one. Okay? Now, I don't mean to be overstating this, but my understanding of it, there was a lot of advances going on in astronomy and other things like this in 17th century and before. Before, people had assumed the Earth was the center of the universe. Okay, everything revolved around the sun. Around the Earth. The sun rose in the east and set in the west. It's going around the Earth, right? The moon rises in the east and sets in the west. Though at a different rate than the sun, it goes around the sun. The stars in the sky, if you look at them, the North Star stays pretty much fixed, but everything else tends to go around it. So it's like they're going around the Earth. Okay? So scientists, philosophers, just assumed we were the center of the universe. They were like teenagers, right? Never mind, I won't say that there. Okay, so there were some problems, though. There were these little other things out there that didn't follow the stars well at all. They looked like stars, but they weren't. They were planets. And the reason they got the name planets was they didn't follow the pattern of the stars. They kind of drifted across the sky sometimes. Sometimes they followed the stars fairly nicely. Other times they didn't. They wandered around some. And the name, the Greek name for wanderer was planet, or something that sounded like that. Okay? So, here came a pretty powerful Egyptian astronomer named Ptolemy, and he came up with this really complicated formula that accounted for the wandering of the planets. Okay? Did a little bit maybe with the moon too, but did that, but after a while it fell apart. And they kept trying to perfect this, trying to make it make sense. And then along came this guy named Copernicus. Ever hear of him? He was a Polish clergyman, actually, and he proposed, hey, I don't think the Earth is the center of the universe. The sun is. Now, he wasn't quite right there either, but the sun is the center of our solar system. He was right on that one, not the center of the universe. But that wiped out the need for all those complicated calculations that they were doing with Ptolemy's method. Well, Copernicus didn't quite have it right either. He, and still people think in terms of this, he had everything in these invisible spheres that circled the Earth. Okay? The moon was on its sphere, the sun on its sphere, the planets on their spheres, or whatever, and are circling the sun, I should say. And the stars were way out there on fixed spheres. Okay? Hard to say. Well, along came another guy named Edmund Halley. There were some problems with those spheres. They didn't match the data either. Okay? And Edmund Halley came along and he proposed, with very, very careful measurements, that the planets did not circle the sun, they ellipted the sun. They weren't in fixed spheres, they were on ellipses. The sun was one of the focuses of the ellipse. The other wasn't, and then everything started falling into place. All the astronomical data seemed to fit a lot better. Okay? The trouble is, no one knew why. They knew it fit. All these other models had problems. This one seemed to fit, but no one could say why they fit. And that's where Isaac Newton came along, And he didn't need average rate of change like a secant line. He wanted a tangent line. And of course, and we'll get into this, that's why he started that. He was also a physicist, so he was interested in velocities and acceleration. Again, not average velocity or average acceleration, but instantaneous velocity and acceleration, which went right back to the planet circling the sun. He needed that as well. And then later, he, I think, realized that it worked also for max and min problems, which we'll see. And then later, area. Actually, one of Edmund Halley's laws of planetary motion dealt with the area, and you needed that as well. So differential calculus here, integral calculus there. Each problem involves the notion of a limit. Oh, we love our limits, don't we? And calculus can be introduced with any one of those four problems. Again, the first three, differential calculus, the fourth one, integral calculus. What does it mean to say that a line is tangent to a curve at a point? Okay? Essentially, the problem of finding a tangent line at some point P boils down to finding a slope of a tangent line at point P. It sort of seems like it's redundant here. Here's how we're going to approach this. I think it's probably how Newton did it, possibly even Leibniz, I don't know for sure. You can approximate that slope by using a secant line. So here's what we're going to do. Here's a curve. You can imagine that is the curve of a planet, okay, going around the sun, an arc, okay? Now, if you want to talk about this, the slope of that arc, you can approximate it by a secant line. If here's your point C right here on the x-axis, this is f of C up here, and you go a little ways away from C, and they call that a delta x. Have y'all run into this notation before? Delta means difference, okay? A little bit beyond x. This is x equals C. Go a little bit beyond that equals C, and now you're at C plus delta x. Just a little bit further, okay? So now you're out here. Here's x equals C. Here's your delta x. Here's C plus delta x, okay? Right here. C plus delta x right there, okay? Then this point up here is going to be your function at C plus delta x, okay? Now, if you want the slope of that secant line, it's change of y over change of x, right? That's what a slope is. Change of y, delta y, over delta x. That's where you've had deltas before, right? Slopes, change of y, delta, difference in y. So here we have this change of y here is f of C plus delta x minus f of C. That's the length of that little segment there. F of C plus delta x minus f of C, that gives you that length there. That's your change of y. Your change of x is C plus delta x minus C. Well, that's just your delta x, okay? Now, there's your slope of your secant line. Is that the slope at any point there? Well, actually it is, but that's not the point we're interested in. We're interested at this point. That's not the slope at that point. The slope at that point would be there. But you can't do a secant line there, okay? That's where you do your tangent line. So how are we going to approximate the tangent line using these secant lines that we know how to do, okay? This is a slope. 2 points, change of y over change of x, okay? Well, here's what we're going to do. We're going to let that delta x get smaller and smaller and smaller. So the next time we'll do a point down here, and that will be the slope of the secant line. Then we'll do one down here, and then one here, and we're going to let that delta x approach 0. But guess what? If the delta x is approaching 0, your delta y is also approaching 0. So what kind of form do we have? Second? Indeterminate form. So then there may be a limit there. And if there is a limit, that's going to be the slope of the tangent line. Okay? That's our approach on this. Okay? That slope of the secant line doesn't give you the slope of the tangent line, but the limit as delta x approaches 0, that could happen. All right. So if CF of C is the point of tangency, and C plus delta x is that a little bit further there, and alpha C plus delta x is a little bit further up there, is a second point on the graph of F, then the slope of the secant line through the 2 points is given by substitution into the slope formula. That's your y2 minus y1. There's your y2. There's your y1. x2 minus x1. There's your x2. There's your x1. The difference there. And I've already said this is alpha c plus delta x minus alpha c. That's your change of y's. And then your change of x's is c plus delta x minus c. Well, minus c plus c is 0. That just gives you a delta x here. So the slope of the secant line is alpha c plus delta x minus alpha c divided by delta x. Change of y over change of x, slope of the secant line. The right-hand side of this equation, I guess that's the one we talked about, is a difference quotient. Do you remember that from Cal 1? Pre-Cal? Difference quotients. You had them, whether you remember them or not. You did have them. Difference quotient. Difference here, quotient there. Okay, difference quotient. The denominator, delta x, okay, is the change in x, that little bit that you increase the x by, and the numerator, the delta y, is a little bit that the y changed by when you increase the x a little bit. Okay? That's your change of y. There's your difference quotient. All right. You can obtain more and more accurate approximations for the slope of the tangent line by choosing your points closer and closer to the point of tangency. Your point of tangency is down here. Your x plus delta x is over here. Alpha of x plus delta x is here. Let that delta x is closer and closer and closer. You're approaching the point of tangency. So, all right. This time, boy, they're sort of doing it backwards here. I guess it doesn't matter. Okay. Here you're letting your delta x be a negative value here. Here's your CF of C, and you're letting this be a x equals C minus delta x. It's over here, and then you're approaching this way. Let this value get closer and closer to that one, and you see your secant line is here, then it's here, then it's here, and ultimately it becomes your tangent line as the delta x is getting closer to 0. Over here, they let the CF of C be here, your delta x is positive, delta y would then be a positive value too, and here your slope of your secant line is here, then it gets closer here, then it gets closer there, and ultimately becomes a tangent line there. As you let your delta x get closer and closer to 0, there and here. Okay? So that's your tangent line approximations. So guess what you're doing? A limit as the delta x is approaching 0. That's why we did the limits. So here's the definition of a tangent line with slope m. If f of x is defined on an open interval containing some point c, and the limit as delta x approaches 0 of delta y over delta x, that's your slope, would be the delta y is alpha c plus delta x minus alpha c, y2 minus y1, over c plus delta x minus c, that would just be your delta x. There's your slope of the tangent line. It's a limit as that delta x approaches 0. If that exists, if that limit exists, then the line passing through CF of C with the slope of m is the tangent line to the graph of f at the point C of C. Again, this would be an indeterminate form. If this is getting smaller as that's getting smaller, they're approaching 0, you can have a limit. If there was a discontinuity there and this never got any less than this, but this got closer to 0, that would be some value over 0 that would not exist. So the slope of the tangent line to the graph f at the C, f of C, is also called the slope of the graph of f at x equals c. Okay? Slope of the tangent line, x equals c, or the slope of the graph at that one point, x equals c. So here's example 1. I haven't been keeping up with where we were in the text. And by the way, there's a feature there on Isaac Newton. Has to be one of the most incredible minds ever to have existed. I mean, he changed all of physics in his lifetime. He changed all of mathematics in his lifetime. He defined optics in his lifetime. No one else understood that before him. He defined gravity in his lifetime. No one else did that. I mean, he changed so many things. One man, okay? So he's a potential paper topic. But if you read this first page, page 100 here, you'll see several other people listed. Pierre de Fermat, René Descartes, Christian Huygens, Isaac Barrow, and Gottfried Leibniz, in addition to Isaac Newton. So all these people made major contributions to calculus. Isaac Newton is usually given most of the credit, but he's not the only one. All right. Now, there are some figures in your book that don't show in the slide set. Sorry about that. I wish they had. But use your book or ebook or whatever you're using. All right. So we did the definition. Now on page 102 is example 1. To find the slope of the graph, f of x is equal to 2x minus 3, where c is equal to 2, you can apply the definition of the slope of a tangent line as shown. Okay? Now, if I could get you to sort of wipe the fuzziness of calculus away, and I just ask you, what's the slope of the function f of x equal to 2x minus 3? What's the slope of that? Never mind, we'll get there, okay? Now, they chose c equal 2. I wish they'd have chosen something other than c equal 2. Just too many 2's in here, we'll see that. But let's apply the definition of the slope of a tangent line, okay? So, all right. Let me get my pen set up. Okay. What is that definition of a tangent line? Do you remember what it was? I'll go back a slide or two to remind you. Well, I'll try to, there it is. There is the definition of the slope of a tangent line. Got it? Okay. Well, they're doing it for you. I'm sorry. I wish. Yeah. They'll do it. So, yeah. If you go back, it's f of c plus delta x minus f of c divided by delta x. Okay? Well, here, the c is 2. So c plus delta x would be 2 plus delta x. Okay? So it's f of 2 plus delta x minus f of c, which is f of 2, and we're going to divide that by delta x. Okay, so what we've done is just do that. So what I want you to do is you figure out what f of 2 plus delta x is. Here's f of x. What is f of 2 plus delta x? You tell me. Okay, that would be 2 times 2 plus delta x. You plug in what is there. Minus, well, where did my pen go? This is sort of aggravating. The pen just quit writing. There it goes. Minus 3, okay? All right. So this will be the limit as delta x is approaching 0 of f of 2 plus delta x. So let's just go on and figure out what that is. What's that?
I said this is kind of why I started getting confused. How come the two, there's two outside of parentheses?
Okay. All right. Good question. Here is your f function. It takes the number 2, multiplies it by the x, and subtracts 3 from it. Well, up here, instead of x, we're putting 2 plus delta x, right? So it'll be 2 times what's inside here, 2 plus delta x minus 3. That's why I said there's too many 2's here. I wish they'd have chosen something other than 2. That'd be 4, or 7, or 18, or something else. But this is, you're plugging in 2 plus delta x everywhere you see an x here. And you see it's 2 times 2 plus delta x minus 3. Okay? So do the math. What would that be? Distribute. That would be 4 plus 2 delta x minus 3. Okay? Do the math. That would be what? 1 plus 2 delta x. Okay? So that would be 1 plus 2 delta x minus f of 2. Well, now let's do what f of 2 is. And what would that be? Two times, say again? 2, okay, the x is 2, minus 3, and that would be 1, okay? 4 minus 3 is 1. Okay, so minus 1 over delta x. Got it? Make sense? Okay. Well, what does that numerator give us? 1 minus 1 is 0. So that'd be the limit as delta x approaches 0 of 2 delta x over delta x. And what happens there? Delta x's go away. Because delta x over delta x is 1. That would be 2. Okay? Now, they did the same thing. I wanted you to do it, not just do what they did. They put in 2 times 2 plus delta x minus 3 minus 2 times 2 minus 3 over delta x. And I think I'm probably going to have to erase mine, otherwise you won't be able to read it. So you ready for me to erase? Okay. Oh, okay, I could have gotten it in there. 4 plus 2 delta x minus 3 minus 4 plus 3. Okay. Okay, they could do it that way. Now you look at this and say 4 minus 4 is 0, minus 3 plus 3 is 0. You're left with 2 delta x over delta x. There we have it. Now the delta x go out, x's go out, and that leaves you 2. So the limit of 2 as delta x approaches 0 is what? Second? 2, of course. So that limit is 2. Now I go back and ask you the same thing I did before. What's the slope of that function up there? What kind of function is that? Linear function. And what's the slope of it? 2. mx plus b. M was 2. B was negative 3. Who cares? That's not what we're looking for. You could have looked at that and said, oh, this slope's going to be 2. Okay? Now, that had nothing to do with c equal 2. They just chose that as a value there. I wish they hadn't, because it gets too many 2's in there and you think they're related. They're really not. But the slope of that is 2. Okay? Which should make you feel warm and fuzzy inside that the slope of a linear equation is the slope. Okay? And it is. It definitely is. Okay. So the slope of f at c, alpha c, where c is 2 and alpha c, we already did that. That was 2 times 2 minus 3 is 1, 2, 1. That slope is m is equal to 2. Okay? So if you drew this thing here, x, y, and when x is 2, y is 1, you got that by plugging in, okay? If we had drawn this on out here, there's -1, -2, -3. Sure enough, that's going to intersect down here at -3. They don't make it big enough, but the slope of that is 2, okay? Because it goes up 2 for every 1 it goes over. 2 over 1 is 2. Always, okay? It doesn't have to be just one value. It could be any value you put in. So the slope of a linear function is the slope of that linear function. That should make you feel good. Okay. So the definition of the tangent line to a curve does not cover the possibility of a vertical tangent line. Why not? That one, the slope was +2. You could have a +3. You have a 1/2. You know, you're 1. Okay? Why couldn't you have a vertical tangent line? Second? Okay, there's a very good reason it's not a function, because the vertical line fails the vertical line test, right? Another way to look at that, you have a change of y here. What's your change of x here? No, vertical. Change of y would be this. Change of x would be 0. So it'd be 7 over 0. Guess what? Not an indeterminate form, an undefined form. So yeah, it doesn't cover vertical tangent lines. There aren't. I mean, you can have a vertical tangent line, but your definition of the tangent line to a curve does not cover that possibility. So for vertical tangent lines, you use the following definition. If f is continuous at c, and the limit as delta x approaches 0 of alpha c plus delta x minus alpha c over delta x, if that's infinity, okay, remember that. Doesn't have a limit. It's an infinite limit, yeah, but that's what we call it. If that's infinity or negative infinity, and guess what? Can you tell which is which? If you had a vertical tangent line, are you increasing this much for a 0 slope, or are you decreasing that much for a 0 slope? You can't tell. It's definitely positive or negative, so we don't even go there. Then the vertical tangent line, x equals c, passing through c alpha c, is a vertical tangent line to the graph of L. So in other words, x equals c is a vertical tangent line of anything passing through the point x equals c. That's what it is. There is no limit as far as your limit formula goes, your slope formula. So here's an example of one of those. The function shown in this figure has a vertical tangent line at c alpha c. Okay? And by the way, you probably are not going to run into these, but in case you ever do, this is a curve often called a logistic curve. Okay? Things that this could model is diseases. Let's say the flu pandemic, if we had one. I don't think it's quite a pandemic yet. When there's no exposures to the flu, you don't have any cases of the flu. But then once you start getting exposures, then it starts going up, and at some point, it becomes almost big time. I mean, it's just increasing. But then once everybody's been exposed and nobody's left to catch the flu, it levels off again. So a lot of times diseases follow this function. It's called a logistic function. You don't need to know that. I just was explaining while we were here. Okay, but it does have a vertical tangent line because at some point there, if you have a little bit of change of y over a little bit of change of x, it's going up big time in y and almost nothing in x. That's an influence slope there. Okay, so that's a vertical tangent line. Another example of this would be the square root function. It has a vertical tangent line at 0. You know, that would be, remember, it's like a sweeping parabola. A parabola is like this, has a horizontal thing. If you flip that over, that would be a vertical tangent line. So there are other examples of vertical tangent lines. Most of the time we say they don't exist. They say infinite. It's a vertical tangent line. That's what it is. It has no slope. It has an infinite slope. Okay. So when the domain of F is the closed interval A to B, okay, counting A, counting B, somewhere in there, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and the limits from the right for x equal A and from the left when x is equal to B. Okay? To me, that sentence by itself is kind of nebulous. Okay? They just sort of pulled it out of the air here. But it's true. I mean, what it's saying is true, but it just sort of seems like, where did that come from? Okay. Now let's see. Okay. They did not do example 2. Let's go on and do example 2. All right. Okay. Find the slopes of the tangent lines to the graph of f of x equal to x squared plus 1 at the points 0, 1 and negative 1, 2. Okay? As shown in the figure, they don't show the figure, so we'll just deal with it. Okay. Now, let me just tell you a little quirk about me. There's lots of quirks about me, but one, I always like to check and make sure what they're telling me is a well-posed problem. So let's say they say this point is on this curve. Let's see if it is. When you plug in 0 for what? 0 for x. Always x, y pair. 0 for x. When you put a 0 in here, what your y becomes? 1. Yeah, so that works. How about this one? When you plug in a negative 1 for x, that would become a, yeah, 1 plus 1 is 2. Didn't know we'd be doing such high level math today, okay? So yeah, both of those points are on this graph, okay? I always like to verify that before I start doing a problem, because if they weren't, then you're trying to prove something that's not, it can't be true. And those are true, okay? Now what it says is find the slopes of the tangent line to the graph of that function. Now this is not a linear function, that's a quadratic function. So what's your definition going to be? For the slope of a tangent line. M is equal to, I'm actually going to call that slope of a tangent line, TAN. What was that limit? Okay, it's x. For the first one here, is x is approaching 0 of f of x. I won't even write that down. Okay. Probably I should write it down. F of x plus delta x minus f of x, probably not doing this the best way, over x plus delta x minus x, right? That's a little sloppy, but can you live with it? So what we could do is just go on and put in your 0. Oh, that didn't work, did it? A 0 there and there, because that's what your zeros are, because x is approaching 0. I don't know, is this helpful to you? 0 plus delta x minus alpha 0 over 0 plus delta x minus 0. Because your x is approaching 0. Okay, so I'm just going to plug in 0 for the x. Well, what is that? What is your alpha 0 plus delta x? Say again? Okay, that would be delta x squared, right? 0 plus delta x is delta x squared plus 1 over, well, no, that's all. Okay, sorry. Okay. And what's your alpha 0? Say again? No, you don't have any delta x's in there. Alpha 0. Plug in a 0, what do you get? 1. Okay. So this would then be delta x squared plus 1 minus 1 over delta x, right? Because that's what you get if you add and subtract 0 to it, right? Got it? You see?
I got confused because of the formula. Yeah, me too. Where did you get the 0 plus delta x?
Okay. Let's go back to here. Okay? Oh, that's the vertical. Let's not do that one. Let's do this one. Okay. All right. I did change things a little bit on you, so I'll go back and do it this way. The delta x is what's approaching 0. That's in your denominator. And this was then alpha of x is x squared plus 1. No, it was plus 1 or minus 1. Plus 1, okay. So let's go back and do it that way. Okay. So, all right. Let me erase it all and start over. Okay. Here's our formula. Okay. Your slope of your tangent line is equal to the limit as delta x approaches 0 of, oh, wait. I erased too much, didn't I? Let me put this down. F of x is equal to x squared plus 1. Okay, and we're at these 2 points, 0, 1 and negative 1, 2. Okay, so this will be f of x, goodness gracious, my brain's not working well today, sorry. X plus delta x minus f of x. And this is all over delta x. Okay? Now, the first x is going to be 0, and that's what I was trying to do before. So let's change this. Goodness gracious. Nope. Okay. Change those to zeros. Okay. All right. 0 and 0. Okay. So this will be the limit as delta x is approaching 0 of, what's your f of 0 plus delta x? That was just delta x, so that would be delta x squared plus 1, right? Yeah, we're run out of time. So this will be delta x squared plus 1 minus, and what's alpha of 0? 1. Okay? And this is divided by delta x. Okay? And what do we have here? 1 minus 1 is 0. So this would be the limit as delta x is approaching 0 of delta x squared over delta x. That would just be delta x. Okay? And what's the limit of delta x as delta x is approaching 0? 0, right? Because delta x is approaching 0, you plug in a 0 here, and a 0 here, right? Okay. So that's your slope when at the point 0, 1. And if you look at the graph, you'll see it has a horizontal slope. No change of y for any change of x. That's the slope of 0. Vertical slope is huge change of y for no change of x. That's vertical. Horizontal is 0 change of y for any kind of change of x. Okay, so that's what that one is. And if you did it the other one, that would be m, the slope of the tangent line will be the limit as delta x is approaching 0 of f of negative 1 plus delta x. This time your x is negative 1 minus alpha of negative 1 over delta x. That's your definition of that when you plug in x equal negative 1, or your c is negative 1. So what does this give you? Well, we're out of time. We'll pick up and do this one next time. Sorry, I was going to try to rush it through, but that's probably not a good idea. So we will do the B part here next time. Let's see if I can find it. Okay, I'll figure that out. Let's see if there's enough homework, if there's any homework exercises here. Do number 5. I think you can do that. Number 7. Any of the odds 9 through 13. All those are at Calc Chat. 11's at Calc View. I think you can do any of the odds 15 to 27. All are at Calc Chat. 17's at Calc View. And you might try doing some of the odds 29 to 35. They're all at Calc Chat. 31's at Calc View. And we'll stop there and pick up the rest of those next time. Let me then pause